Okay, so now we will be in Maya for a bit, going through these points. We'll walk through the model. I used some reference images to create this engine. It's not accurate. I'm sure that the pipes that I have created don't probably make any engineering sense, but they looked real enough in the images, and I just followed them. Rigging, which is basically the spinning of the wheels and the piston that pushes in and out. We'll look at that. We'll import this, or the imported of the scene from Synthise. We'll look at that and how the engine was animated on the tracks, which is basically just as I said in the last video, pushing from one side to the other for most part. Lighting is image-based lighting in Mental Ray, so I'll show you that. And then rendering in layers. I think I did beauty layer, I did ambient occlusion layer, and shadow for the ground. Right, so let's look at the model first. This is the model, and you can see the image-based lighting dome or the sphere in the back. And that, let me just put something on focus here so that I don't lose the engine. Right, so this is how I have created the engine. You see here that has the wheels, and there are two sizes of wheels. One is the one in the front, and then 4 in the middle are same size but slightly bigger, and then you have some wheels in the back which are exactly the same size as this one. What else? The polygon model is just like any other model. I've created somewhat of details so that it would look cool. Some pipes here and there, and some bolts to indicate some details. I've created a door here also, and that door is properly hinged, but I don't think that I have actually used that. You can actually see how this door opens and closes, but that's about it. The rigging part is pretty interesting here. So if you look at the piston, let's see, if you look at, let me go further back so that you can see where the piston work actually is happening. So right there, you see the piston is pushing in, and then as I go further, it comes out. And that right here in the middle, let me just put a little pencil so you can see right here. So that's the head of the piston that's going to push in and push out when the when I scrub through the timeline here, and you see that. And that's just bone structure. I just did inverse kinematics, just like how you would use it for for characters, and I just used it for this workflow. The wheels themselves are spinning based on the actual math. So depending on the size of the wheel, it will complete the circle in that same way that the perimeter of the wheel would. It's just 2 pi r. That's the formula, and I connected that formula to the transform of the engine, which is this node here. And that transform, as it goes from one end to the other, moving the whole engine, the wheels would spin as much as they need to, and I'll show you how I did that using the expression. But before I go there, here's the problem. If you look at this wheel, its scale is 1, and then if you look at this wheel, its scale is also 1, and that doesn't make any sense because they are both obviously different size, but the scale is the same. So I couldn't use the scale as a factor in the formula for 2 pi r or for the radius or diameter. I had to actually use the measurement tool, and this happened because I had already done the freeze transformation on both of the wheels. So at their respective sizes, their individual scale was 1, and that wouldn't really work. But let's look at how I created the motion there. So I have created this small tire just to demonstrate the expression process that I used for that. Now I have some expression here that I'll just delete first, and then we'll walk through the entire thing. Yeah, so let's look at what we want to spin, which is the wheel itself. And the wheel we want to spin in which direction? So that will be rotate X direction that we want the spinning to occur. So in rotate X, if I go to edit, create an expression there, and it's going to be rotate X, which is already there. Now I'll copy this and put it in my notepad where I'm going to create the expression. So what should this spinning look like? Well, the rotation should be 360 degree would be basically the entire rotation. So I'm going to start with 360, and then I'll multiply that with the movement of the driver, which is this node here. So depending on how this driver moves, let's say it's moving like this, then I want that to have some effect, because the distance that it is traveling will be a fraction of the entire perimeter of this wheel. So 360 is the total spin if it moves enough to complete the entire perimeter. But if it's in between, then it should have a fraction of that 360. So I'm starting with 360 as how much I want to spin, and then I'm going to connect that to this driver. So the direction that this is going in is Z direction right here. So what I'm going to do is go to translate Z, take this expression out, or the parameter out, and then copy and go back to my expression builder here times this. And let me just leave it at that for now and see what happens. So if I take this entire expression and go back to my expression window and build that expression right there and create. So let's see what just happened. So if I take this and move it, yeah, so my wheel is spinning. It's not going anywhere, but it's spinning. But I don't know if you notice it, it's spinning extremely fast, meaning that for every small move, it's completing 360 degrees, which is not what we want. We want it to slow down. Now, how much do you want it to slow down depends on how big the wheel is, because that's how the parameter of the wheel would work. So let's take a naive approach and say it's the scale of 1. So let's say this is actually radius, and the radius of this wheel is 1. So what I want to do then is let me go to my expression 1. Yeah, so what I want to do is divide it by 2 pi r, right? So 2 times pi is let me just delete history here of all of this and clear this. Now let's build. Okay, so 22 divided by 7 is pi 3.14 times 2, right? Because it's 2 pi r times 2 is 6.28, and times r. R is diameter, which is or radius, which is let's say 1 in this case, because that's what we are working with. So times 1. I don't really need to do that, but I think I messed it up. Let's try again. Clear, and 22 divided by 7 times 2 times 1. So that's the value that I came up with. So if I take this value and use that as my denominator here in this formula and edit it, let's see what just happened. So if I take this and if I move it, now it has slowed down for sure, but has it slowed down enough? Well, Okay, so I think what we need to do is move the wheel along the direction that the driver is moving. So we need to build another expression which is going to be moving the wheel. So if you take the wheel and say which direction am I moving, so that's translate Z. So if I go into, let's see, expression, I'll just write it right here, and this time it's going to be tire group translate Z is equal to, and it's still going to follow the driver, so it's going to be driver null dot translate Z. Right now I'm not sure if I'm supposed to put the semicolon here, but I'll do it anyway. Yeah, so now let's see, it looks like the wheel is moving, but is it moving properly? It is moving but not properly, because you can see that it's spinning faster than the way it should. It looks like it is sliding on a sheet of ice or something. So we need to fix that. Now it's moving too fast. Basically, we need to slow it down. And how do you slow it down? Well, we use the radius as 1, and obviously that hasn't worked. Our formula is correct because it is well established formula. So radius must not be right. So if I go into create and create a measurement tool, and I'll do the distance tool. We don't need to be very precise for this example, but I'll just create one point here and another point here at the top of the wheel, and that looks like it's 14.137 something. So I'll change the denominator value here, and it will be based on that new radius. So if I go to delete everything and rebuild, so 22 divided by 7, so that's 3.14 times 2. Well, actually 2r, right? And what we have here is the diameter, so we don't need to do 2r, we can just do diameter. So it would be times let's see, 14.1371, call it, and that comes to 44 I'll just take 4 digits after the decimal. And if I copy that and use that in here as denominator and edit, so now let's see what happened. I need to get out of the tool first. Okay, so now let's see what happens. If I move it, does it move properly? It looks like it is getting a traction on the ground properly, and this is exactly the method that I use. Now here is a problem with this method. I'm going to move this slightly up. You will see why in a minute. If I take this group and scale it, and this is the problem that I ran into. Let me just make sure that I'm in scale in the world. If I scale this like this, now let's see what happens if I move this driver. Does my wheel move properly? And if I go, it doesn't look like it's moving properly because it's a little bit sliding. I'll prove it by getting even larger than that. And now if I move it, you can see that the spinning is faster than the actual motion, and the reverse will happen if I scale it down. So right now it's 2.388. If I scale it down to 0.5 and focus on the wheel, and then if I take this, sorry, that's not the one I want. I want this driver here. So if I move it, you can see that it's dragging, right? It's not moving properly, and that's because the radius of the diameter of the wheel is no longer 14.137. We have changed it. So if you look at where the 14.137 is, it's about this distance, and we are a fraction or half of it or something. So how do you fix that? Well, what I did in my engine is I took this entire formula which was working at the correct scale, and I divided this by tire group dot scale. And it doesn't matter which scale I use. You can use X, Y, or Z because they're all going up or down at the same time, when you're scaling the wheel. So let's say X, and then edit. Now what will happen is if you move it, now the wheel is again moving properly. So now it is scale independent. You can have the scale of 2, and when you move it, it will move properly because it's adjusted in this formula now for the scale. So that's how I worked the rigging part in the engine, and that's what you see when I bring in the actual engine. That's what you see when I go through the timeline. Both of the wheels, the small and the big, are moving properly. It's dragging. I think you probably don't see the smooth motion here. Let me go to this layer here, because there is no image and it will show up properly. Yeah, so this is how all the wheels are moving. Now, just to prove the point that I just made about the scaling, if you go in here and go to expression, these are all the wheels, by the way. You see that I'm dividing everything by that scale. That was important. And for the other wheels that are smaller, I just multiplied the entire operation by the scale so that it would properly conform to the actual math based on the size, because I knew if this is 1, then this is 1.75 times 1. That's how I had modeled the wheels anyway. So that came in handy when I wanted to use the formula. Yeah, so that's the rigging part. We talked about the model. There are a couple of other things that I have done. If you look at the light, you see this little object here in front of the light, and that is the object that I basically cached out as Alembic cache and brought it in Fusion so that I can have a location where the light is going to be. The same thing, I did this at the top for the smoke 3D particles in Fusion that would follow this object from the transform node standpoint. And again, Alembic cache for that also. And I also did one for the steam on this side here. And that I created it here, but I ended up releasing steam from down here, because when I saw some of the footage, it looked like the steam would actually come from the bottom here. So then I just offset the location of the 3D particle in relation to this object, which I already had brought into Fusion at that point, and just adjusted the location that way. We'll talk about that in Fusion in the next video. That's that. And the rendering, as I mentioned, it's indirect lighting with this image that I brought into Maya, and it's mental ray, and these are the passes or the layers that you see here. I did the beauty layer, I did the occlusion, which is ambient occlusion layer, and then I did the shadow layer for the shadow of this engine on the ground. Now you see that I have created the tracks here, which I didn't really need to, and also you will see that I have created some poles here. So if you go to the camera view, here you will see that those poles are actually staying where the actual poles are. So you see these two poles here, that's where the actual poles were. And I also have created the ground plane. The idea here was that if I was going to use world position layer that you see here, in that case I would need those items, but I haven't, done that yet, and that's why I created those. But that's where the track marks that I had put in Synthesize helped me a lot here in getting the right location. Yeah, so one last thing is this name. You can see here it's just the image plane, or a normal polygon plane. I just named it station name number 1, and then you see this is station name number 3, and there is 1 2 here. There is 1 2, and then this one actually I can delete it here because I this wasn't created in Maya. What I did is in Fusion I took this plane and just slid it around so that I can cover that sign. Yeah, I think that's pretty much all that there is to talk about. Let's go into Fusion, where most of the action is happening, and the script is quite elaborative. So we'll walk through each node tree and see how it works. Thanks a lot.